Thank you very much. So first, I would like to thank the organizers for allowing me to speak for the first time in a Eurostrings conference. So I will be talking about the paper I released last year with Elias Kiritsis and Francesco Nitti, and Elias is here somewhere in the audience. And this paper was about confining theories on spacetimes with positive curvature. You might have noticed that in nature, quarks do not appear as free particles, but instead they are confined in bound states known as baryons, which are made of free quarks, for example, protons and neutrons. Of course, there are also other confined stable bound states, but these are the ones we see in everyday life. And this fact that quarks at low energies do not propagate as free particles is known as confinement. And it's made possible by the fact that quantum chromodynamics is a strongly coupled theory at low energies. In addition, QCD exhibits another interesting feature, is that at high energies, it becomes a free theory. And this implies that there exists a deconfinement transition. So what does this mean? So let's say we have a gas of baryons and we heat it up. When we heat it up, we put energy into the system, taking the theory to its high energy regime, and it will break the baryons apart. So there will be a thermal phase transition from a confined phase of a baryon gas to a deconfined phase of quark-gluon plasma, where the quarks and gluons are freely propagating particles. Now, this deconfinement transition can also be driven by quantum fluctuations instead of thermal fluctuations. And in this case, it's a quantum phase transition which happens at zero temperature as a function of some other parameter instead of the temperature. And one way to do this is to put the theory in a box. So if you imagine putting the baryon gas in a small box, only small wavelengths will fit inside, corresponding to high frequencies and high energies. So this is a way to probe the high energy sector of the theory. So what will happen is that if you start with a big box and then compress the gas, at some small volume, the gas will deconfine into a quark-gluon plasma. And this is a quantum phase transition now driven by quantum effects. And this is the topic of this talk. We will study deconfinement transitions at finite volume at zero temperature. And the way we obtain finite volume is by putting the theory on a spatially compact de Sitter space. And in addition, in this talk, we will only work in Euclidean signature. So the de Sitter space will actually be a Euclidean sphere with some radius alpha, which controls the size of the box. And furthermore, we will focus on strongly coupled large gauge theories so that we can use the holographic duality as a tool to study these transitions. And this means that we don't have any quarks in the theory, and by confinement, I mean these glue ball bound states, which are kind of confined bound states made of gluons only. So we assume that the quantum field theory we consider arises from an RG flows from some strongly coupled fixed point UV conformal field theory. So near this fixed point, the action of the QFT takes this form where we have the action of the CFT plus some relevant deformation with a relevant scalar operator whose scaling dimension is smaller than d. And here lambda is the relevant coupling, and zeta is the metric of the background sphere. And so given these two length scales that we have available, we can form a single dimensional curvature parameter, R. So here we have alpha, which is the radius of the background sphere, and then this combination here is the length scale associated with the relevant coupling. And now at large curvatures, meaning that the sphere is very tiny, the radius is very small, this probes the high energy sector of the theory, like I said, that only high frequencies fit inside the box. And small curvatures, meaning that the sphere is very large and looks approximately flat. This is the low energy sector of the theory. So basically, this dimensionless curvature can be used as a parameter to parameterize the energy scale. And this point of view was used in holography in these two papers from a few years ago. And a lot of focus on in general, in quantum field theories, in positively curved spacetimes, has been put by these authors, which is an incomplete list in the recent years. So kind of the new thing of this work is that in the infrared, we assume that the theory is confining instead of, for example, flowing to a infrared fixed point. And what I mean by confining is that it exhibits confinement in flat space. And the theory is set to exhibit confinement in flat space if the Wilson loop has an area law. So this corresponds to a quark-antiquark potential glowing linearly at large distances. And we cannot apply the Wilson loop directly as a criterion on a compact space because there's no space to take the Wilson loop to be arbitrarily large. All right, so here's the outline of the talk. So first I will introduce the holographic model that we use to study these deconfinement transitions. I will classify the gravitational solutions of this model and then finally draw the phase diagram. So we consider a bottom-up model for a confining quantum field theory in d dimensions, and this means that the bulk theory will be d+1 dimensional. And we will consider a Euclidean Einstein scalar theory with this action. So it's Einstein gravity minimally coupled to a scalar field phi with some potential v of phi. And this scalar field phi is dual to this relevant scalar operator, which drives the RG flow. And we assume that its scaling dimension is larger than d/2 to be in the standard quantization in the bulk. And so what we will do is we will look for back-reacted domain wall solutions of this theory, where the domain wall slices are spherical. So more precisely, the metric takes this form, where u is the holographic radial coordinate, and then we have some scale factor a, which is the only degree of freedom of the metric we consider, and then phi also has this simple dependence on the holographic radial coordinate. And now we have to choose some potential, because this is a bottom-up model. So first we will choose that at phi equals 0, there's a maximum with a negative cosmological constant. And around this maximum, there's a mass term for the phi field whose mass is fixed in terms of the dimension of the dual operator in the standard way. So this means that this describes the UV fixed point. And so for the holographic radial coordinate, this is reached when it goes to -infinity, where the scalar field goes to 0 with the non-normalizable and normalizable mode in the usual way. And the metric in this u goes to -infinity is an asymptotically locally ADS metric, where the conformal boundary is now this sphere on which the dual theory is living on. And so that was the phi equals 0 behavior. And at large phi, we assume that the potential has exponentially diverging asymptotics. So basically, the potential starts at some maximum and then diverges to -infinity exponentially. The exponent is positive and this coefficient is negative, so that it indeed goes to -infinity. And what this does is that there will exist kind of a soft wall. So if you were to solve for the metric given this potential, you would find that the scale factor shrinks to 0 size at some finite value of the holographic radial coordinate, and the space ends. So the Euclidean solution ends there. And why do we consider exponential asymptotics? Well, the reason is that this will make the dual quantum field theory confining. In particular, it was shown based on these two papers that if the exponent of the potential is larger than this BC and smaller than this value, then the theory exhibits confinement in flat space. So more precisely is that if you look for domain wall solutions with flat slices in this Einstein scalar theory, and you compute the holographic Wilson loop given a solution, then you find that it exhibits an area law in this case. So this Wilson loop can be computed as some Nambu-Goto action of a string wall sheet. And this kind of potentials with these exponents also arise naturally from dimensional reduction of pure Einstein gravity. So if you consider d+n+1 dimensional domain wall geometries with SD times Sn slices and dimensionally reduce over this Sn, what you get is Einstein scalar theory with the potential, exponential potential, with the exponent given by this expression. And for dimensions greater than 1, you find that this exponent here is exactly in this confining regime. And in this context, also this upper bound for the exponent is known as the Kupser bound. So basically only these exponents have an uplift to pure Einstein gravity. Okay, now I will classify the gravitational solutions of Einstein's scalar theory here. So there are 3 distinct types, which are type 1, type 2, and type 3. And they're classified how the scalar field behaves at the end point of the geometry where the spheres shrink to 0 size. For type 3, the scalar field is finite at the end point, while for type 1 and type 2, the scalar field diverges logarithmically to infinity at the end point. So this is kind of a schematic of what happens. So for type 3, there's a regular infrared endpoint for a finite scalar field, while for type 1 and type 2, basically the scalar field runs to infinity into a singularity. And in addition, this type 3 and type 2 each come with 1 integration constant. So they form kind of 1 parameter families of solutions. And then this type 1 solution is a unique solution that sits in between the type 2 and type 3 solutions. So the type 1 can be reached from either side. And this has a nice picture from the uplifted point of view, where the type 3 solutions uplift to this kind of geometry where the SD corresponding to, which is the sphere where the quantum field theory is living on, shrinks to 0 size in the bulk, while the type 2 has the internal sphere shrinking to 0 size, and type 1 has both spheres shrinking to 0 size at the same time. So here we see that even though, for example, type 2 has a divergent scalar field in the downstairs theory, it still uplifts to regular pure geometry in higher dimensions, and it's regular from the higher dimensional point of view. So now I will talk about the phases. So the quantity of interest to us is the renormalized Euclidean path integral, defined by this expression, and it's only a function of this dimensionless curvature parameter, which is the only dimensionless quantity available. And now, in our case, we are looking at large N strongly coupled theories, and this means that the holographic duality relates this path integral to the Euclidean gravitational on-shell action. So what you have is a relation of this type, where this logarithm of z we call the free energy. And what one has to do is one has to solve the equation of motion in the bulk with such that they give the correct dimensionless curvature on the conformal boundary, and then search over all possible bulk solutions, compute their on-shell actions, and pick the solution which has the smallest on-shell action to compute the free energy. And this means that there will be competition between solutions, meaning that there might be kinks in this free energy, and they would correspond to phase transitions as a function of R, quantum phase transitions. So in our case, we have this type 1, type 2, and type 3 solutions, and the type 2 and type 3 have 1 integration constant, and this integration constant is fixed by giving this R on the conformal boundary as a boundary condition. And what happens is that either there exists only a type 2 solution for a given value of R, or only type 3, or both, and then they compete, and one has to find which has the smaller on-shell action. And generically, in our case, what happens is that for small values of R, only type 2 solution exists, while for large values, only type 3, and then in the middle, where you have the type 1 solution corresponds to some fixed value of R, there's some overlap regime. But this already means that because only one of the solution exists in different values of R, there must be a transition from type 2 to type 3 as you increase R. And this is the holographic realization of the deconfinement transition as you decrease the size of the box of the dual quantum field theory. And this also shows that the type 2 solution corresponds to the confined phase of the theory, the large box, while type 3 is a deconfined phase corresponding to a small box. And this one can also confirm by studying the spectrum of fluctuations around these solutions, and the fluctuations around the type 2 solution are discrete, describing the confined glue ball bound states, while for type 3 it's a continuous spectrum. Right, so what we showed is that analytically that there exists a special value BE, which we call the Efimov bound for this exponent B, which is above the confinement bound. And it plays an important role in the sense that it controls the nature of this phase transition. So we showed analytically that if the exponent of the potential is above the Efimov bound, then the transition, deconfined transition between type 2 and type 3 solutions is always first order, meaning that the derivative of the free energy is discontinuous at the transition point. While if you go below the Efimov bound, then the transition can also be higher order. So the way we looked at this was we studied the vacuum expectation value of the dual operator as a function of R. So R is here on the horizontal axis and the wave is on the vertical axis. This dot here in the middle is the type 1 solution, and this red curve is type 3 and blue is type 2 solution. So what you can see here is that above the Efimov bond, there is kind of a spiral around this type 1 solution, meaning that the wave is a multi-valued function of the source or of this dimensionless curvature, meaning that there will be a first order phase transition from one spiral arm to the next. This actually has kind of approximate discrete scaling, which is known as Efimov behavior. But now, below the Efimov bound, there's two possibilities. So the first one is that the wave is still a multi-valued function of R, and there will be a first order phase transition. But the difference here to this first case is that there's no spiral. But the second possibility is that the wave is a single valued function of R, and in this case the transition will be second or higher order, and we will able to show that it's never infinite order, so it's not cannot be a smooth transition. So here's a schematic again. So if the type 2 and type 3 solutions overlap as a function of R, then the transition will be first order, while if they don't overlap, then it's going to be second or higher order transition. And we studied this in a concrete numerical example. So we took a potential given by this expression here. This has the property that at phi equals 0, it gives you a maximum, and then at large phi, it diverges to minus infinity exponentially. What we did is we solved the equation of motion of Einstein's scalar theory numerically and computed the on-shell actions and the corresponding free energies numerically as a function of R. And we did this in 4 dimensions for the dual field theory. And here's a plot. So this is the free energy as a function of the dimensionless curvature of the dual field theory. So here on the horizontal axis is R and vertical axis is the free energy. And this is below, this is above the Efimov bound for some fixed value of B for the exponent of the potential. So what we find, or what we see here is that the type 2 solution exists for small values of R, as I explained, and the type 3 for large values, and then there's some overlap region. And if we zoom in on this region, we see that there's this classic swallowtail structure and a first order phase transition happening at this dashed line where there's a kink in the free energy corresponding to this first order transition. So indeed, this confirms numerically the analytical expectation. And we also see that the type 1 solution sits here, and it's always thermodynamically not favored compared to this type 2 and type 3 solutions. Then we also consider the value below the Efimov bound in this case. Now the plot looks very different as expected. So the type 2 solution is again here for small values of R, for small curvatures, and for large curvatures we have the type 3 solution. And then if we zoom in here where the type 1 solution sits, we get this plot. And now you see that basically the free energy is continuous. So the derivative looks to be continuous, so the transition is at least second order. There's some overlap region here, but this is a numerical artifact due to numerical noise. And what should happen exactly is that there's a type 1 solution sitting here, and then the type 2 branch ends exactly at the type 1 solution, and then the type 3 branch continues, and the transition happens across the type 1 solution. And according to numerics, we also find that it's a second order and not a higher order transition. So the second derivative of the free energy is discontinuous. So to conclude, we demonstrated this expectation that a deconfinement transition can be induced by curvature. In this case, we used holographic to show it. And there's a transition from this type 2 solution to a type 3 solution as you increase R. And then we also showed that this exponent of the potential for large field values plays an important role in determining the nature of this transition. Above the ephemeral bound, it's first order, and below it's first or higher order, and in the numerical example, it was second order. Thank you for your attention.
A very elementary question. So you said that the scalar potential diverges to minus infinity exponentially. So why is that not a problem? Because your scalar Hamiltonian would then be unbounded from below?
Well, at least if you imagine uplifting this potential to higher dimensions, it will turn out to be negative, and the coefficient, so this V infinity, so the coefficient of the potential is minus the curvature of the internal sphere. So it will, so only negative values have an uplift, basically. So from that perspective, it's natural. And also, I guess, the coefficient of the potential interaction was negative for the scalar field. So maybe that also.
No, but yeah, I mean, it's always minus V in the Lagrangian, but in the Hamiltonian, obviously, it would have a plus V, and if the Hamiltonian is unbounded from below, you would have, at least at the quantum level, that's...
Well, this is the Euclidean action, so this should be already the Hamiltonian.
I see, okay, thanks.
Yeah, here. I'm vaguely aware of the similar story in ADS. So you put a theory in ADS and you also use the radius to probe confinement. And there they have, I think, an interpretation of what happens also in terms of the corresponding boundary theory. So it's a non-local, so they don't turn on gravity, but you still have a CFT on the boundary, right? Mm-hmm. And there I think there is a conjecture that the transition is associated with the appearance of a relevant deformation on the boundary or something like that. I don't know if so how does do the two approaches compare, and can you from your approach extract more general lessons for other confining theories?
So I don't know much about this story on negatively curved spaces, but yes, you can generalize this setup to accommodate a negatively curved conform boundary, and then you can study what happens, and that's what Elias has done in a more recent paper as well. So you can look into that if you're interested.